Now let's move forward and look at a different configuration of amplifier. And this is our final example looking at noise. And in this instance, we're looking at a photodiode. Now, a photodiode is a PN junction that has a thin layer of insulation between the P and the N regions, and the electrons and electron flow can be stimulated by the application of photons onto the junction, which causes reverse current to flow. And I've named this the I-photodiode. It's connected to what's called a transimpedance amplifier. It converts current into voltage, and it's dominated by a large feedback resistor like this here. I've also shown a feedback capacitor there, but don't worry about that too much because it's actually necessary for stability for the amplifier, but for our analysis, we will not care about it. When you're doing analysis with things like photodiodes or other current sources, you can assume that the source is actually a constant current source, so you don't need to worry about it. And we're going to calculate out that the photodiode has full shot noise associated with the flow of current because it's crossing a junction. Let's redraw our circuit now and consider all our noise sources around our circuit. We have our current noise, our current, which is I-photodiode. We have a noise current that's flowing into the inverting input of the amplifier. We've got a noise current that's flowing at the non-inverting input of the amplifier. We've got shot noise, which is calculated here, which is 2 times the electronic charge, which is 1.602 by 10 to the minus 19, multiplied by the current flow, the IPD, the photodiode current, and we take the square root of that as to calculate out the shot noise. And up here, we've configured this as a noise current, and this noise current is due to the resistance of RFB. Equally, we could have replaced this by a noise voltage generator in series with RFB, but in this instance we've calculated out as a noise current. And our noise voltage for our amplifier we've placed on the non-inverting input here, which is defined as Vn. Well, we can actually simplify this diagram because we've got a noise current generator here, but it's flowing into a voltage source. And a current flowing into a voltage source can only ever generate 0 volts because the impedance of a voltage source is always 0. So that simplifies our problem here. By virtual earth principle, we can say that the voltage source here can be transferred up to this node here because of the virtual earth. And now we can start doing the analysis looking at the noise current. So our total noise current flowing into the inverting node of our circuit here is our shot noise, which is 2Q times the photodiode current. It's the noise current coming from the noise flowing into the non-inverting amplifier from the datasheet. And it is the noise current that is flowing, that is caused by the thermal noise from the feedback resistor RFB. So we've now calculated out our total noise current that's flowing into the circuit. But you're saying, but what happens about the noise voltage? Well, because we've now calculated this out in current, the effect of this circuit here is a ×1 buffer. In other words, it's a voltage follower. Whatever happens at this node here will happen at the output. So from a voltage standpoint, a noise voltage, whatever happens at Vn will transfer directly with a gain of 1 times directly to the output. So we add that on. So now let's look at our total noise referred to input flowing through our feedback resistor and also the current due to Vn. So we have a total referred to input current, which is noise voltage divided by the square of resistance, because that must be due to the VN signal at the output. We have shot noise here, we have got the noise appearing at the input, and we've got the thermal noise generated from the feedback resistor RFB. Because we're trying to measure the signal IPD, the current through the photodiode, the lower limit of that must be defined by the shot noise. In other words, any signal we want to amplify will have to be larger than the shot noise. So we can state that, saying that we want the shot noise to be greater, and ideally much greater, than all these other noise contributions into this circuit. These two terms here are from the amplifier. The last term is from the resistor. What we can effectively say that in order to make sure that the shot noise is much greater than all the other contributors, that the feedback resistor must be much greater than 4kT divided by 2Q times the current. If we work this out for a typical value of photodiode current of 100 nanoamps, then it turns out that we need the feedback resistor much greater than 510 k ohms in order for that condition to be satisfied. That now completes our noise calculations and noise analysis within electronic system design. Let's summarize how you go about noise analysis in one last slide before we then look at some more practical examples in class. First thing to do is convert your detailed circuit into a noisy amplifier model. Next, always remember you must sum the noise sources as a sum of squares, because all noise sources are uncorrelated. And you can work out the total noise as V1 squared plus V2 squared and so forth. During the analysis, you'll have noticed that whenever there's a small figure and a large figure, the large one always dominates, because we are looking with the square of the figures here. So a good example, if you find a noise that's twice as large as another one, then you should focus on the larger one, because it will dominate the overall effect of the performance of the circuit. This is somewhat intuitive, but when you start doing a noise analysis, you'll discover that you can disregard many of the components and just focus on the large contributors to the overall noise performance. When you're trying to work out the overall effect of noise at the either referred to the input or at the output of the amplifier, the total voltage is the noise spectral density, in other words, the value per root hertz, multiplied by the square root of the bandwidth. And the last point is that noise figure is always the total input referred noise divided by the Thevenin or source noise. And noise figure must always be greater than 1, because any amplifier will add noise onto your circuit. That completes the analysis of our amplifier design, and now we'll look at some more examples of how you can apply this noise theory onto your circuits to design low noise solutions for your projects. Thank you very much.